Welcome, and thank you for being here today. We all understand the importance of automation as a means of improving application process control, and this usually brings to mind images of robotics spraying parts with high precision. But there are other forms of automation that complement both manual and automated applications that improve the process outcomes and thereby increase predictability and repeatability. Today, we're going to talk about these less evident tools and how they can be utilized with bonding agents to improve performance. If you're not familiar with St. Clair Systems, we design and manufacture advanced point-of-use temperature and viscosity control systems for industrial fluid dispensing processes, and we've been doing it since 1990. During that time, we've amassed more than 3,500 active installations all over the globe. Specializing in both recirculating and dead-end systems, we handle low viscosity materials like water and solvents that are less than 1 centipoise, all the way up to high viscosity materials like sealers and adhesives that are greater than 1,000,000 centipoise. To handle these applications, we have to be able to work at pressures from 0.4 bar to more than 400 bar. So who cares? And the answer is lots of folks, as you can see here. This spans myriad industries like automotive, steel, plastics, composites, nanomaterials, food packaging, pharmaceuticals, and sporting goods, just to name a few. Each successful project with demanding customers such as these has increased our understanding of the ramifications of temperature and viscosity in a host of fluid dispensing applications. Yes, this is a shameless advertisement for St. Clair Systems, but since many of these are critical coding applications, it's also the reason we're qualified to be here today discussing this topic. And now, to assist you, we are proud to announce that we have successfully incorporated St. Clair Systems India Private Limited with our home office and assembly plant in Kolhapur. This gives our customers in India the opportunity to obtain Western technology and quality manufactured in India at Indian prices. Check out our website at www.stclairsystems.in. We build a variety of systems to meet every application, from large systems consisting of modules up to 10 meters long, weighing more than 3,000 kilograms and costing upwards of $500,000, to small systems that sit on a tabletop with a footprint of less than 40 square centimeters, weighing less than 15 kilograms and costing less than $5,000. In addition, we have a line of Viscometers, which includes our VTS inline unit. Designed for continuous in-process control, it has no moving parts and is constructed entirely of 316 stainless, so it's compatible with all process fluids. At just 21 centimeters long and 6 centimeters in diameter, it's small enough to fit easily into virtually any dispensing system. This allows you to eliminate the uncertainty of manual viscosity measurements for less than $5,000. So let's look at the fundamentals that create fluid dispensing issues in the first place. We're often asked why we focus on temperature, and the answer is that temperature affects viscosity, which in turn affects flow, pressure drop, volume of the dispense, and the ratio in the case of 2K materials. But most of all, the spray pattern. Here we can see how the spray pattern changes with the width increasing proportional to the temperature, but this phenomenon is actually caused by the change in viscosity. Which begs the question, what is viscosity anyway? A relatively simple explanation is the property of resistance to flow in a fluid or semifluid. Water is the universal definition of a fluid, but what is a semifluid? Honey is a great example. Think of honey when you put it in the refrigerator. It gets thick, very thick, in fact, almost solid. But take that same honey and place it in the sun on a hot day, and the change is dramatic. It thins out significantly, and you can pour it, almost like water. This change in how it flows represents its change in viscosity, and in this case, as we'll discuss a lot today, the cause is the change in temperature. For instance, here we see the viscosity temperature curve for Parker Lord's ChemLock 220, a common solvent-borne bonding agent as measured in St. Clair Systems India's lab. It's the typical curve we're all familiar with, the viscosity falling as the temperature increases. Though it looks like a linear relationship with a slope of approximately 0.9 seconds per degree C, when we apply a linear trend line, it reveals that, as with most modern coatings, This is actually an exponential curve. Another interesting fact is that Parker-Lord's DS3105 datasheet recommends that this coating be applied at a viscosity of 22 to 28 seconds, which is obviously below the minimum value shown in this dataset. This indicates that it must be diluted in order to be sprayed. That same datasheet recommends that this coating be diluted with 25 to 50% xylene. Here we can see the viscosity versus temperature curves for various dilutions of Chemlock 220 as prepared by St. Clair Systems, India. If we project the recommended spray viscosity range of 22 to 28 seconds across these curves, we can see the importance of the interaction between dilution and temperature in the actual viscosity of the fluid. It is apparent that, depending on the temperature, dilutions as low as 5% can be used, whereas dilutions of 25 to 30% on the low end of the recommended range can produce viscosities outside the recommended range. It also seems clear that dilutions greater than 30% will produce viscosities below the recommended range for spraying across nearly all temperature conditions. But it is important to understand that adding solvent alters the carefully developed coating formulation, and this solvent creates many issues with our process. First, this represents excess cost because every drop of added solvent will be driven off in the oven as the coating is cured. In addition to the environmental concerns, it also represents a risk to our operators. To make matters worse, too little or too much solvent can cause defects. We can plot this on a continuum. If we have too little solvent, we get dry spray and all of the associated issues. If we add a little more solvent, we reach the optimal performance level. However, if we continue to add solvent, we start to get cure issues which, as we add more and more solvent, can progress into problems with adhesion, blistering, and even solvent pop. This is why the temperature factor is so important. So, it's important to understand the impact of viscosity in our process. Proper coating viscosity is key to successful process outcomes. Yet even in today's modern applications, we usually make one viscosity adjustment at the beginning of the process, and we usually make that adjustment by adding solvent. And we generally ignore the impact of temperature on our process outcomes. So what factors affect temperature? Well, there's ambient temperature, coating storage temperature, the volume of the source container, the coating flow rate, and the recirculation rate and the path through which that recirculation follows, pressure settings, pump type and horsepower, shear, which comes from pumps, agitators, regulators, nozzles, fittings, etc., and the substrate temperature. It's important to remember that friction and shear equal heat. This is the reason that simply controlling ambient temperature is not effective. Besides, it's also important to remember that often the fluid we're dispensing comes into our carefully controlled process from a totally uncontrolled area. This means continuous changes in temperature and therefore viscosity. So how do these temperature-induced viscosity changes affect Chemlock and primer? It's all about film formation. So let's start with a perfect film. If the viscosity can be controlled and the system set up such that atomization, deposition, and film build are even across the part, the cure will be even and the result significantly more predictable. This more consistent surface will also produce a better bond. Not only will the bond be stronger, but the layer will be significantly stronger as well. But creating a perfect film requires perfect conditions. More often than not, however, conditions are not perfect. As we've already seen, if the fluid temperature is wrong, it will affect atomization, spray pattern, flow out, etc. The result is an uneven film across the surface of our part. This can have a significant impact on our film cure. Here we can see that thinner film areas will cure more rapidly than thicker film areas. This uneven surface will have a negative impact on bond performance. It's also possible to create blisters from solvent entrapment under the cured surface of the coating. Obviously, this will have a negative impact on bond performance. To make matters worse, if the thinner film areas are within spec, the thicker film areas represent excess coating being applied, which equals cost. So, What defects can we attribute to these temperature-induced changes in chemlock and primer viscosity? The same ones you're used to. First, there are the interlayer failures. These are the result of poor bonding between the substrate and the primer and the chemlock and the rubber. Then, there are the intralayer failures, often defined as cohesion failures. It's easy to see how these relate to our temperature-induced film variations. First, we have to start by establishing our dry film thickness range. Per data provided by Parker Lord, primers should be applied at a 5 to 10 micron dry film thickness. The top coat or adhesive should then be applied at an 18 to 25 micron dry film thickness, for a total dry film of 25 to 30 microns. Likewise, a single coat application should be in the 25 to 30 micron dry film range. So now, let's return to our film build example. Here, we can see that we have film thicknesses both above and below the recommended 25 to 30 micron range. Accentuated by the unevenness of the surface, the areas with insufficient film will be more difficult to bond to and will be prone to interlayer failure. Conversely, the areas with excess film will be subject to intralayer failure because the excess thickness compromises the strength of the layer. In order to get a predictable film repeatedly, the goal must be to stabilize and optimize the viscosity of the coating material at the point of use, which, in spraying systems, is the nozzle orifice. No other material temperature in the system matters to the stability of the coating process. So how do we manage that? Here's an example of our bonding agent temperature control system installed on an automated spray system. It's the perfect solution because it's both low in cost and small in size. It is capable of both heating and cooling as required, so the fluid temperature will always be correct regardless of changes in ambient temperature from morning to night and season to season. Its low power consumption makes it economical to operate on a production basis, and we utilize our patented recoilable coax hose technology to carry the temperature control all the way to the gun to establish point of application control. And it works for manual applications too. So, when is temperature and viscosity control necessary? When dispensing a viscous material sensitive to temperature changes, when manual, automated, or robotic equipment is used, when repeatable results are desired, and when quality requirements are high. In short, always. So, take your bonding agent layer from this to this. The benefits include improved quality, increased first pass yield, reduced bonding agent usage, reduced primer usage, reduced solvent usage, reduced rework costs, reduced scrap costs, reduced warranty costs, reduced environmental impact, and reduced operator exposure. So, again, I want to thank you for taking the time to be here today. Though we've only scratched the surface of what temperature and viscosity control can bring to your bonding agent application operation, I hope that we've opened a new window through which to evaluate your process.